Good morning, everyone. Wow, that's loud. My name is Brendan Hassett. I'm a professor of mathematics at Brown University, and I'm very pleased to introduce Tony Anthony Várilly-Alvarado for this invited lecture. So Anthony Várilly-Alvarado received his undergraduate degree at Harvard and went on to do a doctorate degree at Berkeley under the direction of Bjorn Poonen. But I really got to know him when he took his postdoc at Rice University. I was privileged to be his colleague from 2009 to 2015, and I can say with certitude that the best thing I did in my years at Rice was recruiting Tony. He was a wonderful collaborator, and a lot of my best work in arithmetic geometry I did because I learned from him, and a wonderful colleague, and the best lecturer I knew in all my years at Rice. So I think you're in for a treat. Let me hand it over to Tony for his lecture. Thank you.
Good morning. Hi, everyone. Thank you, Brandon, for that heartfelt introduction. So I want to thank the organizers for giving me the opportunity and the platform to share with you a few vistas of the kinds of mathematics that I do. I want to thank you for coming here this morning. It's great to see you all. There are a lot of friends and colleagues that I see as well, and it always reminds me that it takes a village. I've worked very hard, but I could not have been here today if it weren't for the effort and the faith that a lot of people put in me and the opportunities that they gave me. So thank you very much. So with that said, let me actually start with a quote that I really like. This is David Foster Wallace, who's one of my favorite authors, and it goes like this. So it says, "There are these two young fish swimming along, and they happen to meet an older fish swimming the other way, who nods at them and says, 'Morning, boys, how's the water?' And the two young fish swim on for a bit, and then eventually one of them looks over at the other one and says, 'What the hell is water?' And this talk is about water. It's trying to understand the natural habitat and the context of certain problems that on their face look like number theory problems, and they are number theory problems, but the way to access them and to think about them is informed by a different sort of part of mathematics, a different habitat, and that's geometry. So with that said, let me start with three questions that I really like. So the first one, which has received a lot of attention in the last year, is which whole numbers can be expressed as the sum of three cubes? The second one is about a box, and it asks if there is a box such that the distance between any two corners of this box is a positive whole number. And the last one asks, is there a 3x3 magic square of squares? And I will review what a magic square of squares is very soon. But these are the three problems that we're going to use as we explore some ideas in Diophantine geometry. All of these questions are questions about whole numbers, about integers, and they ask about algebraic relations between whole numbers and integers. So they're very properly sort of number theoretic questions, but each one of them has an avatar as an algebraic surface, and the geometry of that algebraic surface really sort of tells you at least what you ought to expect the answer to this question to be. And I'm not a huge fan of surprises, so I will say that we don't know the answer to the bottom two questions yet. So, and unfortunately, I will not be answering one of those two questions today. I wish I were, but we have made some progress, and I will tell you a little bit about that as we go along. Okay, so the first of the three questions was about sum of three cubes. So what you want to do is you want to fix an integer n, and then you want to ask if there are integers x, y, and z, such that x cubed plus y cubed plus z cubed equals n. Okay, so this is which whole numbers can be expressed as the sum of three cubes, and x, y, and z are allowed to be negative, and this makes the problem pretty hard. Even if n is positive, what can happen is that x is big, but then you make y negative and it cancels out some of the stuff that you already see coming from X, for example. So let's just sort of try a couple of these. So, how about 35? And so maybe I can ask for some audience participation. I promise this one's not a curveball. Yeah. 320, I heard. That sounds good, right? 3 cubed, right? Plus 2 cubed plus 0 cubed is 35. Great. Let's push it down a little bit. How about 34? Yes? Negative 1 cubed plus 2 cubed plus 3 cubed. Correct. That's great. In fact, that's a much better answer than the one I had. So thank you for that. So I had this one, 5 cubed plus 5 cubed minus 6 cubed, which also works. Yes. It's funny, you think it's like, oh yeah, this one must be the smallest one, and yeah, there you go. Thank you for that. That was awesome. So, okay, so we push one more down and say, okay, how about 33? And I used to give versions of this talk where I would say, well, this is an open problem. But last year things changed, and now this is no longer an open problem. We actually have an answer, and there it is. And that's the smallest one, as far as we can tell. And so, and it's very difficult. You will not find this solution by using brute force, exclusively brute force methods. So you have to be somewhat clever to do this. And Andrew Booker at the University of Bristol came up with ideas to sort of reduce the space of possible X, Y, and Z's to look at, and actually manage to find this solution. And I think this is the sort of problem that captures a lot of our imaginations, in a sense. And so we keep going, and how about 32? And so, okay, 33 was really, really, really hard. It turns out that 32 is actually impossible. But it's much easier to prove that it's impossible. Because what happens is that when you look at cubes modulo 9, an integer cube modulo 9 can only be 0, 1, or 8. And 32 is 5 modulo 9. And you cannot get a combination of 1, 0, 1, and 8 to add up to 5, zeros, 1s, and 8s to add up to 5 modulo 9. And so there is sort of what in the business we call a local obstruction to the solution. And we'll come back to that a little bit later. So when a number, so 32 had this property that it left a remainder of 5 when you divide it by 9. If you leave a remainder of 4 when you divide it by 9, you get the same kind of issue. You cannot get 0, 1, and 8 modulo 9 and combine 3 of these things to get a number whose remainder upon division by 9 is 4. And so it's impossible to actually solve the equation x cubed plus y cubed plus z cubed equals n when your number leaves a remainder of either 4 or 5 when I divide it by 9. Okay, but barring this, there's a conjecture that was, the first statement of it that I can trace back, it goes back to Heath Brown in 1992, who basically said, well, that's it. If you have an integer that doesn't leave a remainder of 4 or 5 when I divide it by 9, then that integer should be expressible as the sum of 3 integer cubes, in fact, in infinitely many ways. And I should say, I spent some time reading that paper in preparation for this lecture, and I think, and Heath Brown admits it in that paper, that at the time, it was a bit of a bold conjecture to make, but our understanding of algebraic surfaces has improved enough since 1992 that this conjecture actually makes perfect sense today, in the sense that there's, not only is there more evidence, but the kind of heuristics that we have really support this conjecture that Heath Brown made. And I'll come back to this problem once we set up algebraic surfaces a little bit. So the second problem that we talked about, the box such that the distance between any 2 corners is a positive integer, is a problem that is sometimes ascribed to Euler, but I should say that in some sense Euler didn't quite look at this problem. He was interested in a box where most of the distances between two corners were integers. But if you look at that long diagonal labeled z on the cubed, he didn't look at that diagonal. He asked for a box where x1, x2, x3, y1, y2, y3 were positive integers, but he was agnostic about whether z needed to be an integer or not. And so that's the problem that he really did study. But this is sort of a natural extension, and in fact, there are boxes of the sorts that Euler was looking for originally, but we have not found a box where, in addition, this long diagonal is also an integer. And I will try to explain why it's reasonable to suspect that there is no such box. Okay, so, and then the last one was about magic squares. So a magic square, you see one here on your right, also on the left in a pictorial way, is a grid. In this case, it's a 3x3 grid where what you want is that the columns, the rows, and the two diagonals add up to the same number. And the one that we see here is one of the, as far as I know, it's the earliest recorded magic square. And although perhaps it's apocryphal, the tradition has it that around 2200 BC, the Emperor Yu saw this magic square on the back of a turtle. And so this is why you see this, this turtle. The magic squares have really sort of captivated not just mathematicians, but sort of, you know, the public at large, in a sense, and artists in particular, for example. And so here's a painting of Albrecht Durer. I hope you can see that. It's called Melancholia 1. It's from 1514. And, well, if you look closely, up there is, in fact, a magic square in that painting. And it's a 4x4 magic square. So in this case, again, all the columns, all the rows, and the two diagonals, in fact, add up to the same quantity. So what we're looking for is something like a magic square, but we're going to put one more restriction on these magic squares. So what we're going to ask is that we want the entries in our box, in our grid, to be squares themselves. Okay, so here I have 9 variables, x1 through x9, they've been squared. And I would like it to be the case that, for example, x1 squared plus x4 squared plus x7 squared is the same thing as x1 squared plus x2 squared plus x3 squared, and so on. So I want the same properties that I wanted before. So all the rows should add up to the same number, all the columns should add up to the same number, the two diagonals should also add up to the same number. And this problem was, in fact, first considered by Lucas in this form in 1876. And he tried very hard to come up with a magic square of squares, and he came up with a few near misses, but it didn't pan out. He couldn't find one. The problem was sort of revived by Martin Labarre in 1984. And then it was very much popularized by Martin Gardner in the Math Intelligencer in 1996. So Gardner refers to Labarre as sort of the person who asked this problem, but it turns out that in fact Lucas had been looking at that well before. And one thing that I should point out is that we're looking for sort of an honest magic square of squares, in the sense that I don't want zeros in any of my boxes. I don't want to put 0 squared. And also, I want distinct entries, because if I don't ask for distinct entries, then for sure there are magic squares of squares. I can just put 1 squared, 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 and that would do the job. It's not a very interesting magic square of squares. So we're going to ask that these entries are distinct and non-zero. But the fact that there are sort of silly magic squares of squares makes this problem really, really hard. And I'll try to point out why that is as we go along. Okay, so what I want to do is sort of next is a preamble of Ken Ribbett's talk. So Ken Ribbett tomorrow is going to talk about a 2020 view of Fermat's last theorem. I want to show you what the 1983 view of Fermat's last theorem was like. And I'm using Fermat's last theorem as an excuse to explain to you a little bit about geometry of curves and solutions to systems of equations that define curves, because it'll inform how we look at surfaces later on. And since it's sort of one dimension lower, the theory is, and the classification is a little bit more accessible. But I want to use a particular set of curves, and they're going to be given by this equation, x to the n plus y to the n is equal to z to the n. And I'll show you pictures of how these curves can look like in a second. So Fermat's last theorem, as proved by Wiles and aided by Taylor in 1995, says that if you have a triple of integers, x, y, z, such that x to the n plus y to the n is equal to z to the n, and n is at least 3, then the product of x, y, z has to be 0. Fermat's last theorem doesn't say there are no solutions to this, because 0 to the n plus 1 to the n equals 1 to the n. So there are solutions, but it's like a silly solution. So it's the kind of thing that happens with the magic squares of squares. There are silly solutions, but we want to toss those away. So I don't want any of x, y, or z to be 0. Okay, so what I want to do now is, this is what's called the Diophantine equation. I want x, y, and z to be integers, n is an integer. And I want to reinterpret this in a more geometric way. And for that, I have to tell you what the habitat of that equation is like. And this is called the projective plane. So it's less complicated than it sounds. So what I want to do is I want to take the rational numbers cubed, so triples of rational numbers. And so you think of a 3D space, but you've only kept track of rational coordinates in your points. And then I want to remove the origin. So this is what, minus 0, 0, 0. And then I'm going to identify any 2 points that lie on a line through the origin. So if I have 2 points, and they happen, if I connect those 2 points by a line, and that line happens to go through the origin, I'm going to say these 2 points are really the same point. Okay? And this creates what's called the rational points of the projective plane. And so this xyz with colons is what we used as the notation for the equivalence class that we get when I sort of do this identification of my 2 points that define a line through the origin. And so what this is saying is that whenever I take a point, I'm allowed to sort of rescale it up and down. And so for example, if I take the point that has coordinates 1, 1/2, and 3/5, I can take my lambda up there that you see to be 10, and I can rescale the coordinates just by multiplying everything by 10, and I will get a point whose coordinates are 10, 5, and 6. And because there is this witness lambda that shows me that these 2 points lie on a line through the origin, I'm going to say that these 2 points are the same. Okay, so you end up identifying them. And so an observation which comes from what we essentially just did is that whenever you have one of these points, if you have denominators, you can clear the denominators, just like we did just now, right? We had denominators of 2 and 5, and I just multiplied across by 10 and got rid of my denominators. And so if I have one of these points, x, y, z, then I can choose a representative where x, y, and z are integers. And moreover, if they share any common factor, I can divide by that factor. For example, if they all share a 2, then I can multiply all the coordinates of my points by 1/2 and get rid of that extra 2. And so I can assume that x, y, and z are all integers, and I can assume that there's no common factor that x, y, and z share. So this is what'll be sort of the habitat for my curves. As you can see, I need 3 coordinates, x, y, z, to specify 1 point. And Fermat's last theorem uses 3 variables, x, y, and z. And so we're going to put Fermat's equation onto this plane, and on this plane it'll define a nice curve. And then we're going to look at what the geometry of the curves tells us about the solutions that we might expect to the original equation. Now, later on in the lecture, I'm going to need higher dimensional spaces. I'm going to need, or lower dimensional spaces. I'm going to need the projective line. I will need projective 3 space. I will need projective 6 space as well. But once you sort of get the hang of what's going on with projective 2 space, then n-dimensional projective space is not so bad. You need n+1 coordinates. So I'm going to take my q to the n plus 1, I'm going to delete the origin, just like I did before, and I will identify 2 points if I can scale from one point to another. And that's the same thing that we did before. The 2 points are identified if they define a line through the origin in a much larger dimensional space. So in this lecture, we'll use n is 1, n is 2, n is 4, and n is 6 and 8, I think. So we'll get there. Remember, there were 9 variables in the magic square of squares, x1 through x9. And so those 9 variables are going to give me a point in projective 8 space. So that's where this will be going. Okay, so let's go back to the Fermat curves. So we have x to the n plus y to the n minus z to the n is equal to 0. I brought the z to the n to the left-hand side. And the statement about Fermat's last theorem can be rephrased in terms of points in projective 2 space that happens to satisfy this algebraic relation, that x to the n plus y to the n minus z to the n is equal to 0. So Fermat's last theorem is essentially a statement that says that this Cn of q, if you have a point in there, one of your coordinates has to be 0. So that's what this says. So in the top, it's just the last line from the previous slide. So we're taking the rational points of what we call the Fermat curve. And these are points in projective 2 space. So they have to have 3 coordinates to be specified. But I want them to satisfy this algebraic relation that x to the n plus y to the n minus z to the n is equal to 0. And I can just rephrase Fermat's last theorem as saying, let n at least 3 be an integer. If you have one of these rational points on the Fermat curve, then the product of these coordinates has to be 0. Okay, so this is sort of towards a geometric feel for Fermat's last theorem. And so this Cn, this equation, x to the n plus y to the n minus z to the n is equal to 0, defines a curve inside projective 2 space. So you should say, I mean, there's something that feels counterintuitive about projective 2 space, which is we need 3 coordinates for projective 2 space. But because I'm allowed to rescale things up and down, I lose sort of a degree of freedom. And so really projective 2 space is 2-dimensional, even though it takes 3 coordinates to specify a point. And then we've put 1 constraint on these points, and so I go from 2 dimensions to 1 dimension. And so I can think of the Fermat equation as giving me a curve in projective 2 space. And so what I want to do now is say, okay, what does the geometry of curves predict about the equation that Fermat is so famous for? Okay, so for that, we need to review a little bit about geometry of curves. So let me introduce a couple of the key players. These are perhaps not the definitions that you would see in a textbook, but they are relatively digestible. So if I take a curve in projective 2 space, and I want this curve to be nice and smooth, so it doesn't sort of cross itself, it doesn't have some sort of kink. And if it's given by a polynomial, the vanishing locus of a polynomial of degree n, which is homogeneous, as is the case with Fermat's equation. So let me go back for 1 second. You see, in Fermat's equation, you have x to the n plus y to the n minus z to the n. There's 3 monomials, and all of them are of degree n. And that's what homogeneous means, that every monomial that you see has the same total degree, in this case n. And we define the genus of my algebraic curve to be this product. This is n minus 1 choose 2. So n minus 1 times n minus 2 divided by 2. And so if you give me an equation and you make sure that it's nice and smooth and every monomial has the same total degree, and that degree is n, then I can attach this integer, n minus 1 times n minus 2 over 2, to that curve. Okay, and that's called the genus. It has a geometric origin. It's what happens when you look at the set of complex solutions to your algebraic curve, and then you try to see sort of how many holes that set of complex solutions has. And so, because remember that the complex solutions, the complex numbers are sort of 2-dimensional as a real vector space. And so, even though I'm talking about a 1-dimensional thing over the complex numbers can have a more sort of 2D feel when we sort of try to plot the points that we can see. So, and based off of the genus, there is another number called the Kodaira dimension. of a curve. And the Kodaira dimension is one of 3 numbers. It goes from -1 to the dimension of a curve, and the dimension of a curve is 1. So it can only take 3 values, -1, 0, and 1. And you can read off what this Kodaira dimension is just by knowing the genus. So if I tell you the degree of the polynomial that defines my algebraic curve, I can compute the genus. And from the genus, I can compute this number, which is either -1, 0, or 1. Okay. And this number, it wasn't really born this way. I am giving you sort of a rather economical presentation, in a sense. This number is really comes from looking at what are called differentials on the curve, and using these differentials to sort of take that curve and try to sort of smush it into some projective space. And then you sort of see what are the dimensions of the images that I see when I try to do that. So the original number has a much more sort of geometric definition, but it can be approached this way, just from the degree of the curve. And this number, in fact, indicates the Riemannian curvature of the set of complex points on the curve. And very counterintuitively, -1 corresponds to positive curvature, 0 corresponds to flat curvature, and 1 corresponds to negative curvature. It just worked out that way, which is a little sad, but it's okay, because we want to keep that distinction, because things will really go haywire if we don't when you look at higher dimensions. So, okay, so what I want to do is explain to you what it is that we know about algebraic curves if I tell you their Kodaira dimension. So if I tell you the degree of a curve, then you can compute the genus, then you compute the Kodaira dimension, and it's one of 3 numbers. And once I know what that number is, then I can actually start telling you about what we know about rational points on such objects. For example, when the Kodaira dimension is -1, these are what are called rational curves. And what that means is that my curve is really isomorphic to a projective line, and really a straight line, okay? Now, the isomorphism that gets me from the curve to the projective line might involve polynomials whose coefficients are not necessarily rational numbers. I might need, a square root of -5 or something like this to write down the polynomials that would take me from my curve to a straight line. But it happens that if I know that my curve has 1 point, all I need is 1 point, then in fact, I can write down a map and an isomorphism between my curve and a straight line using polynomials that have rational coefficients. And this is just going to be stereographic projection. We'll see it very soon. If the Kodaira dimension is 0 and I have a point, then C is what's called an elliptic curve. And these are really sort of ubiquitous objects in number theory. Euler, okay, this is always a funny statement. Euler showed that the set of rational points on an elliptic curve forms a group. Okay, that's always a little funny because Euler didn't know what an elliptic curve was, and he didn't know what a group was. So to say that he proved that the set of points of an elliptic curve form a group is a little funny. But what he did do is he found these crazy relations between integrals. And today we interpret those relations between integrals that look a little funny as the addition law of points on an elliptic curve. So he really did do it, he just didn't know that he was doing it. And moreover, Mordell showed that this group of points on an elliptic curve is a finitely generated abelian group. And as mathematicians, that makes us very happy because we have structure theorems for objects like this. And so that means that we have some hope of trying to understand a little bit how these points lie on our curve. And finally, if this Kodaira dimension turns out to be 1, these are called curves of general type. And general type usually means we don't know a whole lot. So in 1983, and this is why I have the stop date of 1983, Faltings proved that whenever you have a curve of Kodaira dimension 1, defined, say, over the rational numbers, and it's a nice curve, then there's only finitely many points on that curve. And this theorem won him the Fields Medal. This is a impressive, a monumental intellectual achievement to have done this, prove this theorem. So what I want to do now is take these ideas and apply them to our Fermat curves. Okay, so I'll take you through a little tour of that. So the case n equals 2. N equals 2 is not in Fermat's last theorem. There are Pythagorean triples involved here. But the theory of curves will just give us Pythagorean triples for free, as you will see in a second. So in this case, n is 2. The exponent of my curve is 2. And so when I take n minus 1 times n minus 2 and I divide by 2, I get a genus of 0. A genus of 0 corresponded to a Kodaira dimension of minus 1. And we said this is a rational curve. This is supposed to be isomorphic somehow to a projective line. And we observe that there is a point on this curve, for example, 0, 1, 1. If I take x is 0, y is 0, and z is, x is 0, y is 1, and z is 1, then I get a solution to that curve. And I'm going to use the inverse of stereographic projection to show you how the straight line is actually isomorphic to this curve. And so to do that, I need to sort of bring us back into the world where we're not doing projective geometry, but we're doing affine geometry, just an x and y axis, where we can see what's going on. So what I'll do is, if z is not 0, I can just divide through by z and say little x over little z squared plus little y over little z squared is equal to 1. That's the same equation that I had before. And I'll just relabel capital X is going to be little x over z, and capital Y is little y over z. And so I can just draw this. This equation now says capital X squared plus capital Y squared equals 1, which is a circle. Okay? So in the case n equals 2, we're staring at a circle. And a copy of the straight line that I've promised you is the x-axis in this case. So if you take a point on the x-axis, namely s comma 0, so s is sort of the parameter along that straight line that I look at, I'm going to connect it to the one point that I know. So let me go back for 1 second. The one point that I know is 0, 1, 1. And remember that capital X is little x over z, so 0 divided by 1, so 0. And capital Y is little y divided by little z, so 1 divided by 1, so 1. And so the point that I see is 0, comma 1, which is on the y-axis there. And what I do is I take the point s comma 0 and I join it to the point 0, comma 1. That's the straight red line. And then what I do is I take my s comma 0 and I map it over to the intersection point that I see with the circle. And if we do a little analytic geometry and a little algebra, this is what the coordinates will come out to. And so I've defined a map for you that takes the coordinate s to the two coordinates that we just saw on that picture. And to complete this map to a map that starts off in the projective line, there's sort of a standard trick in projective geometry. The point S in my affine line corresponds to S colon 1 in my projective line. And the point with two coordinates in my xy axis corresponds to taking the 2 points and then taking an extra 1 because we are essentially setting little z equal to 1. And then what I can do is I can clear my denominators. And so I get my 3 coordinates in projective 2 space almost, which are 2s, s squared minus 1, and s squared plus 1. And then there's a standard trick to sort of homogenizing, in a sense, these polynomial functions. I'm taking a little poetic license here, but it works in this case. And so the map from the projective line is one-dimensional, but it needs 2 coordinates, s and t, and I just map over to projective 2 space, where I need 3 coordinates, and this is the map that I use. st goes to 2st, s squared minus t squared, s squared plus t squared. And lo and behold, this map, you can check, is actually an isomorphism. And the conclusion that you end up drawing for this is that every integer solution to the equation x squared plus y squared plus z squared equals 1 has to be of the form that we just found, because I had an isomorphism, except there's this extra k that happens, and that's because I can always take a solution and rescale it. Remember Pythagorean triples, like 3, 4, 5? I would take, 6, 8, 10. I can always take a triple and scale it up and down. That also happens with projective space, and so we have in fact characterized all Pythagorean triples. And so the paradigm here is that geometry really determines arithmetic. This is my favorite proof of the shape of Pythagorean triples. I learned a totally different proof in an elementary number theory class that sort of pushed a lot of algebra around, and then I believed it because I could follow every step, but I didn't understand. And when I saw this, that really made me feel like, it was geometry all along. That's where these funny quantities, 2st, s squared minus t squared, and s squared plus t squared, really come from. So that's n equals 2. N equals 3 was the case of an elliptic curve. And what we said was in the group of rational points on an elliptic curve is a finitely generated abelian group. And so the structure theorem for finitely generated abelian groups tells me that I have this nice finite part, this torsion part, and a free part. And so if I want to look at Fermat's last theorem, in this case, then what I'll do is I'll try to study the torsion part and this free part individually, and you can do that. And you have to use sort of the whole hammer of theory of elliptic curves to do this, but you can show using reduction, what's called reduction modulo p. So you take your equation and then you start, instead of thinking it as an equation in the integers, you look at it, mod 19 or mod 31, and you use the information that you see when you look at the equation mod 19 or mod 31 to try to say something about the original equation. And that's a very powerful technique in arithmetic geometry. And you can prove that in fact there are 3 points on this curve that have finite order, but you see that all of these 3 points have at least one 0 coordinate, which is what Fermat's last theorem was indicating would happen. And using a much deeper theory of what's called descent, you can prove that there is no free part to that abelian group. And so really there are only 3 points, 3 rational points on this curve, and we can write them down, and all of them have at least one 0. And so Fermat's last theorem holds. You can prove Fermat's last theorem for n equals 3 by using the theory of elliptic curves in a completely tight way. And then sadly, so if n is at least 4, then what will happen is my genus is at least 2 and my Kodaira dimension becomes 1. And what we know is that this set of rational points on these curves is finite. So already in 1983, even though we couldn't prove Fermat's last theorem, if you gave me a particular exponent, 19, x to the 19 plus y to the 19 equals z to the 19, Falting's theorem already told us that there's at most finitely many solutions to this problem. But it didn't tell us how many or which ones. It just said it's finite. And so that was the state of Fermat's last theorem in 1983, well before Wiles, for example. So, but the fact that there is a point on this curve makes things really hard. We have a whole slew of techniques in arithmetic geometry to prove that a set of equations has no solutions. Okay? But proving that these silly solutions are the only solutions is much, much harder than proving that just there are no solutions at all. And the kind of problems that we've been looking at do have solutions. For example, if I take x is 0 and y is 1 and z is 1, there is a solution. And so this is part of what makes Fermat's last theorem quite difficult. Okay, so I'm going to leave the world of curves for now and start looking at higher dimensions. And so I'm going to look, for example, at a surface in projective 3 space. So if I'm in projective 3 space, I need 4 coordinates to specify a point. And so, for example, x, y, z, and w. And this equation that you see here defines what is an example of something called a K3 surface. This K3 surface has points. I can take x is 1 and z is 1 and y and w are 0, and that'll work. So there are some points. But in general, when I give you some collection of polynomials, the kind of questions that we ask is, well, can I solve those polynomials in the integers? And so this is the kind of thing that we'll look for. So it turns out that you can't always do it, because if you have a solution over the integers, you must have a solution modulo p to the n for every prime p and every exponent n. And that can actually cause an obstruction. Right? There might not be a solution, just like the sums of 3 cubes for 32, by looking at mod 9, which is 3 squared, so p is 3 and n is 2, we saw that there was an obstruction to actually finding a solution. But an incredible thing is that checking whether you have solutions modulo p to the n for every p and every n can actually be done algorithmically, even though there's infinitely many primes and infinitely many n's to check. So the first step is telling you that actually you only have to worry about finitely many p and finitely many n, and it tells you which p you have to worry about and which n, and then you sort of go from there. It's a beautiful theory that is a consequence of deep work of Grothendieck and his school of algebraic geometry. So sadly, sort of these local obstructions might not be enough. There are systems of equations, like this one considered by Birch and Swinnerton Dyer, where I see 2 equations in 5 variables. So there's 5 variables, so my points are going to have 5 coordinates, and so I'm going to be in projective 4 space. And it turns out that this pair of equations have solutions modulo p for every prime p and every exponent n. But it turns out that there are no integer solutions to this equation. So the local obstructions aren't enough to tell me that there's no, that this equation can't be solved. And so one thing that I want to tell you briefly about, because it was a very cool story, is a theorem from 2014 with Bianca Verai, who is in the audience, and is my mathematical sibling, friend, collaborator. It's been awesome to work with her. So what we did in 2014 was to show that whenever you have a surface that looks a bit like this, so it's 2 quadric equations in P4, there is a way of showing that there are no points by constructing a map from my surface to a projective line in such a way that the fiber above every single point fails to have points mod p to the n for some p and for some n. So let me show you a picture of what this is. That's Bianca, by the way, and that's me. So what happens is that you have your surface x, and you have your and you construct a map to the line P1, and then you look at the preimage of all these blue points. And then you say, okay, I want to make sure that my equation has solutions mod 7 cubed, which is 343, and the answer is yes, you can find a point that's z mod 343z. And you say, okay, I want solutions mod 25. Well, you can go to some other fiber and find solutions mod 25. But if you stick to just one fiber, you can't find points mod p to the n for every p and every n. So in every fiber, there's at least one prime that fails to have solutions. And if there had been a point on my surface, that point would give me a solution in the integers, and that solution in the integers would give me a solution modulo p to the n for every p and every n. And so to us, this was a beautiful theorem because it gave a visual interpretation of something called the Brouwer-Manin obstruction, which is a horrific thing that's defined by using sort of abstract sheaves and cohomology, and you don't, it's very hard to get your hands on these Brouwer-Manin obstructions, but it turns out that for this particular kind of surface, you can really see the Brouwer-Manin obstruction. You can, there's a way of just tilting your vision and chopping up the curve in the surface into curves, and you can just see that every one of those curves fails to have points mod p to the n for some p and for some n, and so your surface can't have points. So this was sort of a very nice little thing. So if you move to surfaces, surfaces also have a Kodaira dimension. This time it goes from -1 to 2. It always goes from -1 to the dimension of the space that you're looking at. And the surfaces are very well classified. And roughly speaking, sort of the lower the Kodaira dimension, the easier things are. The higher the Kodaira dimension, you end up in general type, and things get much harder. Okay, so what I want to do in the last few minutes of the talk is go back to the 3 problems that we had at the beginning, see the surfaces that we have, and try to understand where they fit in this Kodaira dimension regime, and what it is that we can expect to see about the rational points on these surfaces, and therefore the solutions to the original number theoretic problems. So the first one was the sum of cubes. So the sum of cubes has Kodaira dimension, well, okay, this is a little funny. The compact version of this surface has Kodaira dimension -1, but this turns out to not be a compact surface, and so it tends to behave as a Kodaira dimension 0 surface. They're called log K3 surfaces. And in 2012, Collet-Helene and Olivier Wittenberg showed that the obstructions that you would expect account for all log K3 surfaces to have points or to not have points simply aren't there for the sums of cubes problem. And so this actually gave, to me, in my view, this gave a lot of teeth to Heath-Brown's conjecture, because we have a theory and we have an expectation, and it turns out that the surfaces that are defined by the sum of cubes equation fits very nicely with that theory, and we can compute what the expected obstructions are, and we don't see them. But you do have very sparse solutions when n is 6 mod 9, because, so 33 is 6 mod 9. When I divide 33 by 9, I get a remainder of 6. And part of what happens is that you only have, for example, the only way for 3 cubes to add up to 6 mod 9 is if each one of them is minus 1 mod 9. And for a cube to be minus 1 mod 9, the original variable has to be 2 mod 3. And so you're sampling your x's, your y's, and your z's from buckets that are sort of 1/3 of all the available numbers. And 1/3 times 1/3 times 1/3 is 1/27. And so when you sort of try to count all your solutions and you try to look at their density, whatever this number is, there's a factor of 1/27 in it. And so you expect these solutions to be quite sparse. So the perfect cuboid's surface is, well, I haven't shown you how it is a surface. Let me show you here. So if I take a perfect cuboid, I can just write down all the Pythagorean relations that I see on the perfect cuboid. For example, if you look at the rightmost face, you see that x2 squared plus y1 squared plus x2 squared plus x3 squared has to equal y1 squared. That's a Pythagorean relation that you get. And you write them all down, and you boil them down a little bit, and then you see that, well, you have 7 variables. So what you would have is a point in projective 6 space, and they have to satisfy 4 algebraic constraints. And 6 minus 4 is 2. That doesn't always work. I mean, okay, yes, 6 minus 4 is always 2. Okay, I didn't really mean that. But the trick of just sort of subtracting a dimension for every equation doesn't always work, but it does in this case. And so you get a surface, and it's a surface of Kodair dimension 2. And that means it's general type. And the expectations for the distribution of rational points on surfaces of general type mean that we don't expect very much. So there's some deep conjectures of Lang and Voida that imply that in a surface of general type, there are only finitely many curves of genus 0 and genus 1, and that's where we expect to see points. And that outside of these curves of genus 0 and genus 1, there's only finitely many other rational points. And so in joint work with Niels Brown and Jordan Thomas, we took a crack at trying to prove that the surface of perfect cuboids has finitely many genus 0 and genus 1 curves. And this was pretty hard, because this surface, first of all, is not smooth. It has 48 singularities, but that actually, weirdly enough, helps. And if you look at the genus 0 curves, the rational curves, and the elliptic curves that you expect to see there, you can find about 32 genus 0 curves and 72 genus 1 curves. This was done by Ronald van Lauk in his undergraduate thesis. And a lot of the trivial points that you see, because there is such a thing as a trivial cuboid, right? Take the box and take one of the sides of the box to be 0, and you get a rectangle, and then Pythagorean triples exist. So this surface has tons and tons of points, but these points don't define interesting perfect cuboids. And so what we did with Niels Brown and Jordan Thomas recently is we showed that there are only finitely many genus 0 and genus 1 curves that pass through at most 13 nodes. Okay, that sounds a little weird, but it is what it is. But then we also showed that every genus 0 curve has to pass through at least 6 nodes. Okay, and if you could bump that 6 up enough, or bump the 13 down a little bit and make these two things meet, then we would have a proof that there's finitely many genus 0 and genus 1 curves. And I think this is actually a doable problem. We worked on this for 3 years and ran out of steam and feel like maybe we should let other people have a crack at this. And here's what we did. Here are the methods. I think they can be pushed some more, but it's going to take some more work. But that would be really nice, because it would give us some evidence towards sort of the non-existence of perfect cuboids. And finally, I want to go to the magic square of squares. So this was our last question, where we asked, does there exist a magic square of squares? And again, a single one of these squares defines a point on a surface. I need 9 variables, so I'm in projective 8 space. And then I just write down all the relations, right? I want the sum of the entries of the first column to equal the sum of the entries in the second column to equal, and so on. And there are several relations that you write down. It looks like you would have sort of too many relations. You would have 7 relations, but you're setting these numbers all equal to each other. And in fact, it's enough if you know that 3 rows add up to the same number and 2 columns add up to the same number, that forces the last column to also add up to the same number. So there's a little bit of redundancy when you write it down. So when you boil down the system a tiny bit, then what you get is a surface. You only get sort of 6 constraints on my 8-dimensional space. And so you see a surface, and it's a surface of general type again. So the theory of algebraic surfaces would lead you to predict that there's only finitely many 3x3 magic squares of squares. And we haven't found them. And I would personally conjecture that there's not there. Okay? But it would be quite hard to show. And so the very last thing I will show you is that there do exist 4x4 magic squares. Euler found one in 1770. And this is truly an amazing piece of math, because it looks like just recreational math, except he sent this particular square to Lagrange, and with no explanation. It's like, he just said, like, look, you know? And then he presented his ideas of how he did it at the Russian Academy of Sciences. So Lagrange got to peek at it finally. And what he was doing, he was using properties of quaternions. How you take, so the norm of a product of quaternions is the product of the norms, except he didn't know what a norm was and he didn't know what a quaternion was, but he was doing these algebraic relations that expressed these sort of modern day identities. And when Lagrange saw this, he sort of played around with it, and he used these ideas that Euler had used to construct the square to prove his 4 squares theorem. He proved that every natural number is the sum of 4 non-negative squares. And this is one of these pillar theorems that we teach in algebra in number theory, and it comes from looking at a magic square of squares. So, thank you.
So we have a little time for questions. I'm told that you should go to the microphones to ask the questions, otherwise they will not be, sorry. You go to the microphones to ask the questions so we can all hear them.
So I'm curious for the magic squares problem. Sorry. Do we know the status of finitely many genus 0 or 1 curves on that surface?
That's a great question. So the question was, do we know the status on whether there are finitely many genus 0 or genus 1 curves on this surface? And the answer is no. So we, in the same paper with Nils and Jordan, we actually proved something about this surface of magic squares of squares, but the techniques that we have don't really say very much in this particular case. It's a complete intersection of quadrics, and it's singular, but it's not singular enough for our methods to really say something meaningful. So we're still stuck there. Yeah.
Any more questions? Okay, well, let's thank Tony for a wonderful talk.